So, ladies and gentlemen, good morning. We are back to advanced quantum mechanics course. And today I will give you perhaps my favorite lecture in the course about superconductivity and superfluidity. Where we are now? Now we are looking for good examples to illustrate technical side of advanced quantum mechanics. How do we treat the systems of a big number of particles with the help of creation and annihilation operators? And superconductivity and superfluidity provide us very good examples how you could go creative with these operators and how can you describe phenomena which are, well, impossible to describe otherwise. So I will tell you a bit more about superconductors today as compared to superfluids. Well, we just look at definition and physics, how it's been discovered. We understand that attractive interaction actually makes a superconductor, and then we will resort to a method which we have already successfully applied in magnetism a week ago. We will introduce a trial wave function. That will be very fancy, so we need to kind of look at its structure in more detail. Good. After that, we use the same machinery. We take this wave function, which depends on some parameters, which we can tune, and we tune these parameters such that this function has minimum energy. Fine. That's how we find ground state. Then we look at quasi-particles and quasi-particles as a background of this ground state, excitations in this world, in this universe, superconducting universe. We understand symmetry breaking there. Then we switch to superfluids, and I shall say that those are fermions. They're bosons. So the methods are different, and we treat superfluids in a completely different way. I still would like to have an example of field theory, where you just have field operators, nothing but, and that provides us an excellent example for this. Fine. The same, there will be condensate and superfluidity, and we will talk about particles and quasi-particles and symmetry breaking. Good. So today we will have the super lecture about super phenomena. Fine. I see you answer the full questions. Let me perhaps add something about this. There is an idea to have exams in, what was that, beginning of July, offline. Strange motivation that I've heard is that students concentrate more during on-campus exam. Actually, I find it very strange motivation. Usually people are stressed during on-campus exams and could kind of easily remove the stress at home. If concentration is a problem, if noisy neighbors is a problem, why don't you go to the library of that particular university and make exam over there? But okay, we will look at the pool results, and I will yeah, I have to decide it with education administration. Fine. Okay, let's go. Let's go to physics. Let's first talk about superconductivity, and that's been discovered in the Netherlands, unfortunately not in Delft. It's been discovered in Leiden, yeah, more than 100 years ago. And eventually it is a bit interesting story, which I love, how precisely it has been discovered. The point is that superconductivity is something which you cannot really predict, cannot really imagine if you don't know this. If you don't know that superconductivity can occur, you could not imagine it, right? Humans can imagine many things, can predict many things because they just love something, idealize something, and fantasize that it can occur in nature. But nobody would fantasize about superconductivity. It just would not come into human mind. That's kind of illustrated by the history of discovery. So Professor Camarinonis was a pioneer of low temperature research, and he reached low temperatures by pumping, making gases liquid. So it was like pumping factory, which has been pumping for a week or two. And then as a outcome, he had um, several liters of liquid helium, with which he could go to temperatures of about 1-2 K. Right, that was a problem because that helium would evaporate very soon. And that's why in this particular days, he really need hands in the in the laboratory. Good. How one can get hands? Well, it's not that easy. So his solution was to go on streets of Leiden. And as now, there've been kind of young people hanging around. So he invited these young people for little pennies to work in the lab. Was a very creative solution. And once he has seen that that this young person who's been assigned to measure resistance of mercury versus temperature apparently has broken an expensive tool or meter, so the resistance just went down an experimental curve, down to zero. Okay, that young man has been sent back to streets without any payment. But kind of professor has checked everything again, and superconductivity has been discovered. Right. So it's zero resistance, which occurs in many metals and some critical temperature, and resistance is really zero. No dissipation, no resistance for electric current at all. That means that there are supercurrents which can flow in a superconductor without any energy loss, persistent currents, and you can see it in magnetic field expulsion. Perhaps you can see the demonstration of levitating superconductor in magnetic field. It's the same effect. Right. And it's for more than, well, for almost 50 years that the origin of superconductivity has not been identified, right? And it's not because kind of science was not active today. It was very active period of scientific development, of physics in particular, um, uh, relativity theory, nuclear bomb, whatever, right? But it took quite some time to discover the origin of this phenomenon. And the theory, well, one could say that Martin Cooper and Schrieffer has put it as it stands now. That's more or less what I will tell you today. And it's been also discovered that the superconductors provide a case of symmetry breaking. We have seen symmetry breaking by magnets, right? And there are kind of spatial rotational symmetry has been broken by magnetization vector. With superconductors, it's not that simple. It's not really obvious what is broken. It's gauge symmetry which is broken. In fact, gauge symmetry which is responsible for conservation of electric charge, so that the superconductors have superconductors superconduct owing to this symmetry breaking, which has been utilized. So owing to this broken symmetry, superconductors can be used in various quantum devices as a source of quantum coherence. Good. As you can see, I really love superconductivity. I made much in this field during my research career, and I kind of tried that you share my my excitement. Did it work? I didn't see anything in the chat lately. Oh, so that remains unclear to me. Good. That was general introduction. I don't know. I guess everybody of you have heard something about superconductivity. Now let's get to let me call it science. We need to understand how it could happen. And I will sketch you a common cartoon. Which is in principle kind of correct, but there are so many details. If you look at it deeper, that's kind of the relation of this cartoon to reality is roughly as this relation of this cartoon to family life. All right, so let me go through main points of this cartoon. In fact, some metals become superconductors, some do not. And the distinction between these two groups of metals is whether electrons are effectively attract or repel each other. One could say it's rubbish because electrons are charged and therefore they must repel each other. It's not quite true, because it's not electrons in a vacuum we are dealing with. Those are electrons in the crystal lattice. They can deform the lattice around each electron, and then it becomes energetically favorable to come together to the same point and deform it more. let's take some, how do you call it, batute. It's what you find in heaven, and it's big sheet of rubber. Kids come to there and they deform it a bit. All right. Do you see what I'm talking about? You can jump, but let's not consider jumping. It's too complex. It's would be quantum dynamics. Let's take another kid and put it on the same batute. It also deforms the rubber, and you feel already that in fact these kids are attracted to each other, provided they're close to each other. Because yeah, if the rate is if the rate is applied in the same point, deformation is bigger. Fine, that's how attraction can arise. But what this attraction do? They form pairs. They form Cooper pairs, named after Cooper, which was one of the discoverers of superconductivity. It means that electrons come with opposite spins and opposite momentum, opposite wave vectors, to form a pair, which is, let us see, first it is boson. Second, its momentum is about 0. And there's no spin. And actually, the cartoon tells that there are bosons and they form boson condensate. So there's plenty of these Cooper pairs which go to a certain state, certain quantum state at Q equals 0. There's macroscopically many Cooper pairs in this state. It's a kind of fine cartoon, but the problem that Cooper pairs are not really particles. It is important to understand that one cannot really see an individual Cooper pair as a particle which flies somewhere. That's impossible in realistic superconductors. Rather, these particles can live only in the condensate. That shows that there's something wrong with this cartoon, and okay, at least it requires small elaboration. We will not give this elaboration. Rather, we will try different methods without invoking Bose condensate. But anyway, pairs, that is what we will take from this story. And let us express these pairs in terms of our friends, creation, annihilation, operator. Then I understand that these operators, zeta, actually creates a Cooper pair. Yeah, it creates two electrons with opposite K and opposite spins. Cooper pair has 0 overall momentum, but it can come in different sorts, which are labeled by this K. So K is not momentum, the momentum of a Cooper pair, but rather its index. All right. Still see no reaction. Then let me go on, and we'll go on with the formulas. I want to deal with interaction Hamiltonian, and I cannot deal with it exactly, couldn't just solve it. I would uh, I would just sort out the terms and concentrate only on the terms which I like. Right. The question, if a Cooper pair doesn't have momentum, how is a current realized? The Cooper pairs could have momentum, but very small one. Like it could be just of the order of inverse length of the superconductor. So all Cooper pairs in condensate could have momentum of the order of inverse length of a massive superconductor, say whatever, 10 centimeters. And that momentum can be seen as a gradient of superconducting condensate, and that gradient provides the current. So the current in this supercurrent is not a current of dissipative current of electrons where particles with large momentum are involved. It's rather flow of condensate where particles have very small momentum. Right, the interaction. Good. That's usual form of the interaction. You remember there are two particles coming, exchange, and so those are incoming particles, those are outgoing particles created after momentum transfer. Good. So we keep only terms where these momenta are opposite. So that would be K and that would be minus K. So the total momentum of two electrons is zero. We keep only these terms. And right, we also take opposite spin. Then what is there on the left or on the right? We can regard as annihilation or creation of a Cooper pair. If, look, I just rewrite it in this way. There's the same trick with double sum, which one can sometimes um, confuses students, right? So please look attentively at here, and at your ease, understand how this sum can be presented as a product of two sums. All right, but okay, it is the way we express interaction in terms of Cooper pair creation relation operators only, and then we make this summation up and introduce some very crucial parameter, very crucial operator, which we call delta. It will appear to be superconducting order, parameter, and gap in the superconducting spectrum very soon. Good, but now we got all interaction as a product of two operators delta. Fine. And now we go with a trial wave function. This wave function is in fact simple, but rather fancy, and it is. It took quite some fantasy to come up with such wave function, but one can't just regard it as a manifestation of one of the most fundamental property of quantum mechanics, the property that quantum systems can be in superpositions of two states. Right. To understand this, to understand which superpositions are formed, let us first look at something which we know. Let us look at non-interacting Fermi gas and its ground state. Right. We have created, well, remember what is this? We just put electrons up to certain energy, up to certain kF. We have created all these electrons. We could say we have created Cooper pairs. So for each k below k Fermi, we have created a Cooper pair, and we did not create any Cooper pairs for k which are above, which are beyond Fermi surface. And now crazy idea comes to our mind. To create or not to create is kind of binary choice. Like classical bit can only be in two states. Let's make here quantum bit. Let's put each k states is at each k into a superposition of 0 and 1 Cooper pair. Okay, that's what I wrote here. And these variables u and v are coefficients in this superposition. So we have a lot of tunable parameters in this wave function. For any k, we have two complex parameters to tune. Right, there was a question from Sarah. What is the physical meaning of U? Yes, it was previous slide. It doesn't want to go back. This UQ, you mean? As we discussed, it's a Fourier component of interaction potential, so the pairwise potential between particles, which depends on their mutual distance. We make Fourier transform, we go to U. Convenient way to see this is to understand that there's a transfer of momentum Q in the process of this, I could say, scattering. So there's no wonder that this transfer of momentum comes with Fourier component of pairwise potential. Does it answer your question, Sarah? Good. Let's go to the superposition. So now we have our trial wave function, and then whatever, then we can actually check whether it was crazy idea or nice idea. Check with a standard machine array. So as we did for magnetism, we compute the energy corresponding to this wave function, we minimize it with respect to u and v, and see if superconductivity arises. Okay, good. Let us do this program, and to do it efficiently, I need to talk about number structure. So what is this? It is in fact a partition, a convenient partition of the whole Fock space. And the reason to make this partition is that Cooper pairs are created independently within each subspace. I will call this subspace number box. Box big now because it's small, and you can put something inside. So what are states within each box? Well, we have states with no particles at this two levels, k and minus k, with opposite spins. There's a possibility to have two particles. Oh, I missed the brackets here. And also these two levels can be populated with single particles. So I have electrons with spin. I could kind of sketch it like this. So state with 0 particles, state with 2 particles, and 2 states with single electron, either spin down or spin up. All right. It's only a partition. We didn't do anything. Now we will understand how operators work in this basis. The most important operator for us, it is Cooper pair creation and annihilation. And I would forget about these two states for a while. And just consider two states. 0 number of electrons and 2. Then what Cooper pair does, it switches between 0 and 2. It just adds 2 quasi-particles to a number box. Therefore, it's an operator which I put here. Okay, does everybody understand this logic? Does everybody understand? So it's creation, it switches between 0 2, or if it's annihilation, it goes from 2 to 0. Fine. Another operator which I need, just operator of number of particles, and this is diagonal in number box representation. 2 for 2, 0 for the state 0. Fine. With this, we can do all calculations, and the problem is just to sum up over number boxes. But first, we would like to normalize this function. That's easy because it just normalizing individual superpositions. Right, this normalization gives a condition on U and V. So kind of roughly, if they were not complex, I would say that, for instance, V is sine and U is cosine of some angle, and the sum of the squares is 0. Oh, sorry, sum of the squares is 1. Fine, normalization. So this is condition which we have to impose on U and V. Good. Then let us get to the energy. We need kinetic energy. We need kinetic energy. Here it is. I will count energy from the chemical potential. So this small epsilon case are energies counted from chemical potential. Right. Now I can now understand that I have to deal with operator. I looked at it. So the average of this operator is, yeah, computed like this. So there's a wave function of one superposition, conjugated wave function of this superposition. I computed the expectation value of this operator with respect to this wave function. That's what I got. Fine. And I have to sum up our boxes to get the full kinetic energy. Let us see. If I look at this expression, I would say that for positive epsilon, we should be very small. Yeah, as small as possible, 0, 0, 0. I want to reduce energy for each k. But if epsilon is negative, in principle, I could increase v farther and farther, but it stops somewhere. So I could not decrease energy further. So why does it stop?
Because of the normalization function.
It would be good to write to the chart if you know the answer. Yes, Sasha, you're right. This normalization condition of the third, and that suggests that v squared is always smaller than 1, modulus v squared. All right, very good, sir. That means that we stop at 1, right? And then we just see that if epsilon is negative, it's below Fermi level, then the state is filled. Usual non-interacting Fermi gas, no trace of superconductivity whatsoever. Let's see how I'm doing about time. I guess I will go for 6 more minutes and we have a break. Now let us deal with potential energy. Formally, we need to compute the average of this product of two operators. But it's a bit too complicated for me. And I will take advantage of the fact that this operator is a large sum over many, many case states. So it's a kind of like in probability theory. If some random value is a large sum of stochastic variables, its relative fluctuation is small. So I apply some here. I can say the fluctuations of this delta are small, and I can restrict myself to evaluation of single delta only. So I disregarded the fluctuations of delta. This is how it is. If delta doesn't fluctuate, average of its module squared is just a product of averages of these numbers. Good. Then I look here. And yeah, I can eventually compute this average delta. Again, in this case, I need to take two wave functions, u, and put a operator Z. Operator Z has this structure. So it gives a non-diagonal element, product of U's and V's. Fine. It's also nice to notice that U is negative, so potential engine eventually favors superconductivity. U is negative, it corresponds to attraction of electrons. If they repel each other, that doesn't work. Right. So after all, we have computed potential energy. Here it is. Good. Then we have a problem of finding the minimum of this energy with respect to U's and V's at each K. It's not such a big problem because yeah, all this K's contribute independently. So how do I compute minimum? I compute minimum when I vary energy with respect to small changes of V's and U's. So what I have here, I have variation of the energy. However, it's in part right. You see it just minimum. I want to determine the derivative of this function with respect to U's and V's, and set derivative to 0. That will give me the answer. What I wanted to say is that I have to take into account that variations of U's and V's are not independent because of normalization condition. So that's why they are related to each other. And here I have a single variation only. Okay. And that has to be 0. And look, that gives me the relation between U's and V's at each K, which I can solve, again, using the normalization condition. And look, we got this expression for U's and V's in terms of delta. Yeah, but we don't know delta. What is the use of it? All right, we can also, with this use in this, we can compute energy which is accumulated in each number box. Let me get through another slide and we have a break. There's some rather important concept in whatever physics, especially in thermodynamics, and it also comes here. It's a self-consistency property. So we know the expression for U times V in terms of delta, but we also know that delta is a large sum over U times V. So we substitute each other to make sure that these equations are consistent. And we got a single question which contains this delta only. All right, then we will crack it. We want to keep it simple, not only me, but all kind of authors would like to keep it simple at this moment. So we will disregard energy dependence of density of states at Fermi level. We will compute this integral at constant density of states. Then we go from summation to Q of Q to integration over Q, and immediate stage to integration over energy over epsilon. That's what we have. So what I did, I made this integral and I canceled delta in both parts. Yeah, the point that this integral diverges at high energy, and one has to take care of cutoff. This cutoff can be something like Fermi energy. Right, so we put this cutoff here. And that's what we get. We obtain that delta is of the order cutoff energy, or that would be too good to be true, times a factor, times the dimensions factor, which is exponentially small if interactions are small. So it's simultaneously good news and bad news. Good news that this delta, this superconductivity, persists at arbitrary small attractive interaction, right? For magnetism, we did require some finite interaction for magnetic state to rise. Here, superconductivity happens at very small interaction. That's why it's so widespread. But if interaction is small, the energy scale for superconductivity is exponentially small, which means, now let us convert energy to temperature, which means that it can only exist at very low temperatures. And it required, this pumping machinery of Camerlin owners actually to discover a superconductor. Very good, at least I'm done mostly with superconductivity. We will need to discuss particles, and let me have 7 minutes break till 9:41. I will also stir So here we are. We have understood that there is finite delta, finite superconductivity rising at sufficiently low temperatures at any arbitrary small attractive interaction. Good. Let us look at that kind of sets ground state. It means that in the ground state, the particles are in superposition of in each number box. Each number box is in a state of superposition between 0 and 2 electrons. And let us understand how does it change the properties of charged excitations in superconduction. it's a bit of physics, and simultaneously it's a bit of tricking with creation and annihilation operators. Good. So let us see. We have 0 and 2. They're in superposition. They're mixed. So they form two states: ground state and excited state. Now let us recall that in each number box we have also electrons, states with single electrons, and they're not affected by superconductivity whatsoever. Let us see, we can add particle to the ground state and to go to one of the states. Because this ground state has some probability to be a state with 0 quasi-particles, but it also has some probability to be in a state with 2 quasi-particles. It's a proposition. So if we extract quasi-particle, we can also go from ground state to these 2. So those states are obviously excitations, but we can excite the same state either by adding or extracting the particle. That's strange. At least we can compute the excitation energy. That's because we have understood how much energy has been accumulated in the box. So here we have epsilon was original energy accounted from Fermi energy, so it's 0 precisely at Fermi surface, but it comes in combination with square root and delta squared. Right, so it's a hyperbolic spectrum, which I sketched here. Funny enough, if there's superconductivity, one has to pay energy to excite a particle. This energy cost is 0 for normal metal. Energy gap in the spectrum. Let us think of caps a bit. It's kind of crazy that we add and extract energy, add an extract particle and get to the same state. Let us introduce an operator. Let us find it, which describes addition of quasi-particle rather than particle. So it has the following properties. It is 0 if you would like to extract quasi-particle from ground state, because there's no quasi-particle, there's no excitation over there. Right, so for us, it's a definition of the vacuum, if you remember. And if you add quasi-particle with spin up, well, you go to single electron state with spin up. That's logical. Right, to satisfy this two, one has to, how shall I say, tinker this operator and to make it a superposition of creation and annihilation operators. Perhaps you remember we have discussed this superposition, this linear transformations of operators. Max Russ has discussed those in one of the problem-solving sessions. Here's an example. So if we choose gammas in such a way, we got a true quasi-particle operator. it also means that quasi-particles in superconductor doesn't bear a certain charge. They're neither electrons nor holes. They're superpositions of electrons and holes. Okay, there was a question from Sasha. I guess it's already for quite time. Yes, Sasha, you can ask a question about superconductivity. Just shoot. All right, you could also write this question, your question to me if you wish. Let us see. Let us understand this rather mysterious thing, which also brings quantum coherence to our world. Let us discuss this symmetry, broken symmetry. Okay, let me explain this. Did you get gauge transformation in course of electromagnetism? I don't know. Anyway, gauge transformation, it is simple. Gauge transformation is multiplication of a wave function with a phase factor. So we know that all things, all observables contain two size, and this phase factor should cancel for any observable. Let us see how does it work in Fock space. For each particle present, we've got this phase factor exponent I chi. And if we look how operators are transformed under this symmetry transformation, well, they just equalify a factor. Well, again, usually each C dagger comes with C, and this doesn't change anything in the Hamiltonian of the system. That strange sound which I hear. I wonder if yeah, perhaps it comes from my computer. That's not very fortunate. But anyway, let me go on. Sure, but as we have seen, that operators of Cooper pairs, yeah, they also transform with this factor. We understood that the superconductivity is characterized by this number delta. And you see, if you change the gauge, this delta changes. It acquires a complex number. So it really kind of rotates if you regard this chi as a rotation angle. All right. That means that this gauge symmetry, very important symmetry, is broken. And right, so that means that the state of superconductor is sensitive to this phase change. And that kind of makes it macroscopically quantum coherent state. All right. So this is broken symmetry in superconductivity. And let me go on with another super phenomenon, which kind of could have been discovered by Cameron Onnes, but for some reasons it didn't work. It's been discovered by like 20 years after Cameron Onnes made helium electrate. Right. So that's been discovered by in the middle of 20th century, and that occurs in contrast with superconductivity, which occurs in many compounds, elements, materials. It occurs only in two almost identical liquids, in helium. Helium-4 or helium-3. There are different isotopes of helium. Right, and manifestation, it's somehow similar to superconductivity. Superconductors have no resistance, no dissipation for electric current. Superfluids don't have any resistance with no dissipation, no viscosity with respect to flows. What I put here, it's rather old photos, I guess, from this year, when they see a fountain, which would stop if you make it from water. It's not, you know, pumped for fountain. It just they put a vessel with superfluid, put it on the lab table, and the liquid has from this fountain. It goes out without any friction, without dissipation. So it did so till all liquid from this vessel went out. Right. So it's interesting that superconductivity could not be cracked for a long time, but for superconductivity, everybody kind of knew what is that about. Superconductivity happens for bosons. Helium atoms can be regarded as bosons, and it eventually comes from boson condensation, where interaction also becomes important. Gas theory has been made also, I believe, rather early, somewhere in 40s. Good. It makes sense to talk about these two phenomena altogether because it's the same gauge symmetry which is broken. It doesn't give rise to currents of electric currents, the broken symmetry, just because the helium atoms are not touched. But there are supercurrents, as we see, supercurrents of just particle flow. Right. In modern times, there's much more fuss, much more interest to condensation of ultra cold atoms in laser traps, which is in fact the same phenomenon, and it was very popular in last decades. There are many people doing that. But with atoms, you kind of make a condensate of 50 atoms, while here, there's like 10 to the 50 atoms in the condensate. And you get it basically for free. Fine, that was general information about superfluidity. Let us talk about this in detail. First of all, let us consider non-interacting Bose gas, and already here we understand what is going on. Why there is such a strange state, which is considered non-interacting Bose gas with a spectrum. And look at the ground state. If you do homework, you know by heart that all particles in this case prefer to go to one level, and it's perfectly allowed because they're bosons. There could be as many bosons as they want in a given state. Fine. So with fixed this makes a state with a fixed number of particles. A good point is to notice that it does not depend on number of particles, the energy of the system. So all energies corresponding to different ends are the same. And in this case, it makes sense to make superpositions of the states with different number of particles. I put it in this way, these 5 being coefficients of the superpositions. But kind of this model looks too idealized. In reality, there's some interaction, some repulsion, attraction between the gas atoms we are about between these bosons. So let's have some interaction. Let's have some interaction. And first of all, I would like to talk about a framework where we treat superconductivity as we learn and refresh. Quantum mechanics, same quantum mechanical phenomenon can be treated in different ways, different frameworks, different pictures. And since my goal is to give as many examples of second quantizations as possible, I would not do it as with a trial function method, as I did to previous. And also, yeah, there is since we're dealing with fermions, it's time to switch to bosons. What I would like to do here, it's field theory. So we will try to understand the properties of superfluid using only field operators. Again, I don't want to even talk about wave functions. I would like to resort to Heisenberg picture, where wave function is irrelevant, and we just talk about operators. This is Heisenberg equation for field operator. So we'll make field theory, and that will appear to be very simple. In fact, we can use classical field theory as a very good guideline to understand this quantum theory. But let's first make one. Right, so what we got? We have Hamiltonian free particles in terms of field operators. Here we are. And we have interaction. So it's all expressions I've been using all the time, but now for a change, I wrote it with using field operators. One can say it's creation and relation operators which depend on coordinates. Fine. I would like to simplify the interaction. I will replace it with delta function. So it's what we discussed in magnetism. It's contact interaction. Okay, with this, H is collected as this H2 two-particle interaction is collected to this form. Fine. So we have second power in psi, we have fourth power in psi, and we just run Heisenberg equations. Right. This operator has there are two terms in this operator: kinetic energy and potential energy. And kinetic energy gives rise to linear equation. Yeah, that we know. We know that for free particles, equations for operators are linear, which makes it convenient and almost trivial. if we look at the contribution from interaction term, we find a term which looks not that complex. It's just cubic term. But that immediately makes an equation nonlinear. Right, equation for word. It is an equation for an operator rather than number. So there's fancy big matrix which depends on R, and which satisfies nonlinear equation. And yeah, it is not really easy to find a solution to this equation even sorry, to find the solution of this equation in any closed form. It's not impossible even to compute this solution with computers. But fun enough, we can have good intuition and some working platform with this field theory. What is a crucial point? We can eventually at least try to and check what is going on. We can eventually replace this operator with a number. If it is a number, we will choose it not to depend on R. Suppose it can depend on time, but not on R. Why is it so? It's one of the solutions of underlying theory, and this is homogeneous solution. Suppose we regard our superfluid as an ocean, and right, we just consider still ocean, no waves. That corresponds to the ground state. Fine. And right, so what is the justification of such a replacement? It's something which we recently discussed in the context of superconductivity. This operator, in fact, is contributed by a big number of particles in this condensate at 0K. That's why replacing an operator with its average does not look as a bad idea. Fine. So we look just for the solutions of this equation in terms of numbers. Let me look at this equation. So this is gradient. So if you consider, if you look at homogeneous solutions, that just disappears. So the equation would be something like that, which is easy to solve. The solution is just, yeah, one can recall Schrödinger equation, evaluation Schrödinger equation. There's a phase factor proportional to time, and that what you find here is eventually energy. Energy comes from interaction. It contains interaction constant, and this is again this amplitude of the condensate squared. But it's also density of particles. So modulus of this magnitude of this amplitude is eventually density of particles. All right, then this expression makes sense. Mu, it's energy per particle, and it's proportional to interaction and the concentration of all other particles. Yeah. In fact, we reach an important point, but it required so little energy that perhaps we cannot appreciate it. But anyway, it's a solution for ground state of superfluid theory, stationary condensate. And the fun is to look at the excitations. How do we do excitations? That's also rather interesting and specific trick. Eventually, it's not very different from treating ocean waves. So, how do we treat small deviations in general? Just Taylor expansion. Excitation supposed to be a small deviation. So we take this main term, which describes still ocean, which describes amplitude condensate, and we add small perturbation, which depends on coordinate and time. It can be a particle propagating somewhere. And we put it into the equation and linearize these equations, collecting terms of the first order in delta psi. And what's important, I treat this delta psi as an operator. I can do this at field theory, right? So this operator is a large constant plus small operator deviation. Fine. So I make this equation for this operator. It's a kind of linear equation. And I see terms which I like. It's here. I linearized it. I have a term proportional to mu. It's here. It's energy. It seems like whatever. Usual operator equation. Good. I have kinetic energy. This chi-square term. Great. I also have something which comes from interaction. Okay, some addition. That term I really does not like. Oh, okay, I don't comprehend it. And usually people don't like what they don't comprehend. But for some of them, it gives a kick. Eh? Right. So we can try to quantize these oscillations. Remember that those are original particles, those are bosons. So we can kind of regard it as a superposition of boson operators. But yeah, these operators, if I rewrite this equation in terms of operators, I got this this strange term. So normally I have separate equations for B and dagger B, and those terms just mix. B and B dagger, they mix annihilation and creation operators. So how to deal with that? A solution has been proposed by this person. I could not stop telling a couple of words about his personality. A very interesting career and interesting approach to science. Bogolyubov is his name. That might sound Russian to you, right? If you think so, it's a big mistake nowadays because it's actually Ukrainian family name, Bagalyubov. Right, and he's been born slightly before revolution, and in Russian Empire, and it was time of very creative experiments in education. And the man appeared to be a mathematical genius. Like, some kids um, go solving problems much faster than the kids, and that has been noticed. And in fact, he graduated from a university in the age, if I remember correctly, in the age of 15. Everything could go fast by that time, revolution time. He just passed all courses and he got a job. He got a job. One has to recall that in that time, automatic calculations almost didn't exist. And have, you needed to have mathematicians to solve practical problems. What could be practical problems? Modeling of an explosion, trajectory of a ballistic missile, how tank armor reacts on a direct heat. Yeah. Interesting practical problems. And there was how do you solve it? In fact, everything can be seen as a system of nonlinear equations, either in partial derivatives or just in simple derivatives. And there's been many people which have been employed in such a way. Good. So that Professor Bogolyubov has had some experience in this areas, and then at the age of whatever 50 or something, he appeared to be bored. I've been doing these equations all the time. Why don't I do something else? And somebody told him, this new science emerging, quantum field theory, which sounds rather interesting. Okay, then he immediately switched it, and it is his experience with ordinary nonlinear equations, which immediately led him to an idea on how to treat this, how to correct the problem, and how to rewrite it in a harmonic way. Right. So he thought that boson operators of creation of atoms are eventually wrong operators, and we need right ones. And for right ones, we would have a usual form of um, equations for creation relation operators with some epsilons, with some energies of single particle excitations. Right. And how to get from wrong to right, or perhaps one could go back from right to wrong. It is again linear transformation, which mixes creation and annihilation operators, so-called Bogolyubov transform. Good. So how to do this? One can make it operational. One can assume that there are some superpositions with yet unknown alpha and beta, or each k. One has to look at the fact whether these operators, the commutation relations for gammas and for betas are the same. They're again representations of boson creation relation operators. And that boils down to the following requirement. Good. Then would just substitute operators B in the form of gamma to the equations. Let me recall the equation to this equation. And choose coefficients alpha and beta in such a way that equations become harmonic. Okay, that's what I put here. So superposition with yet unknown coefficients. We put it here. And we choose alpha and beta in such a way that equations become correct for gamma operators. That will bring us to some new energies, right energies. So this is energy of quasi-particle creation, not a particle, but a quasi-particle. And gamma is again, as in superconductivity, it's an operator which creates a quasi-particle rather than a particle. Good. So as a byproduct, we have this expression for energy of a quasi-particle. Look, what is this Ek? Let me remind you, it's just kinetic energy of the particle. We have seen it 4,000 times. Parabolic spectrum. That's a massive particle, helium atom. And that mu, that comes from interaction. It's interaction constant times density of the particles. So I just put it in this way to make a compact formula. Again, it's been obtained by using this Bogolyubov-Hanche, Bogolyubov transformation. Very good. Let's just plot it and see what happens. So with red line, I plotted the resulting quasi-particle spectrum. Free particles, I put with a green line. So we see a discrepancy at small k. Which gradually becomes constant at large k. I could make this correspondence, this agreement even better if I add chemical potential to the particle. So there's some kinetic, some interaction energy to paper particle. Good. With this, it becomes almost indistinguishable at BK. So here, quasi-particles are in fact usual helium atoms. Right? I just have one atom more in a certain point in a certain region of space that makes it a quasi-particle. It feels the interaction of all other atoms. That's why its energy bit elevated. Fine. But what do I find here? Eventually, I find excitations with energy proportional to K. And the coefficient, proportionality coefficient, will be some velocity divided by times h bar. Right. So we will look at this dispersion law, these energies in the context of electromagnetic radiation, in the context of photons, light. And here we find it for another massless excitation. Here we find it for sound. So it is almost unbelievable, but it remains a fact. These quasi-particles, these excitations in superfluid, they're pretty well established helium atoms at large Q, and the quanta of sound, quanta of some condensate excitations at small momenta. And this, I would say, completely uh, um, unconnected possibilities are in fact connected in the single notion of Bogolyubov quasi-particle in superfluids. Good. With this, my story is over. Let me get back to the beginning to formulate perhaps some take-home message. So at this stage, we've been doing condensed matter examples for advanced quantum mechanics for applications of second quantization. We talk about superconductivity fermions and superfluidity bosons. For superconductors, we did everything with a trial wave function method. Though this trial wave function was very fancy, it included superpositions of different number of particles. And with this, we could kind of make a consistent theory of superconductors. In fact, all the calculations are taken from this original work of Bogolyubov, Cooper, and Schiffer. Okay, this is trial wave function. We do usual machinery, computing energy and minimizing this energy with respect to parameters of trial wave function, trying to find the best one. We have found fancy quasi-particles, which are neither electrons nor holes, do not have defined charge. One can say that all these fancy things come from symmetry breaking. Then we switch to superfluids. We took it as an example of field theory. And despite the fact that it is a field theory, for ground state, we could get a reasonable solution with almost no sweat. Just Bose condensate. So this operator, field operator, appears to be the operator, appears to be a constant. But as far as we looked at quasi-particles, again, we have seen that distinct from particles might be distinct from particles. And right, that you also do with similar transformation as in superconductors, where you mix creation and annihilation operators. Fine. With this, I would like to stop the recording. It doesn't want to stop. I guess I need to stop sharing. Right, so there was a question for superfluidity, the gauge symmetry was sometimes broken by. Perhaps I didn't stress this. Let us see. Where do we go? Um, so there must be some breaking of gauge symmetry to support these flows, and it's similar like in superconductor. How to express this mathematically? Oh, it's almost here. All right. So if we do the same, and if we look how operators are transformed, we see that this psi, which we use to characterize the ground state of the condensate, changes upon gauge symmetry transformation. It is defined upon a phase vector. It's very similar to superconductivity, and no wonder, because in fact both material systems have boson condensate, as we talked about. Fine. Let us see. I've lost Zoom window, and I guess I have not stopped the recording yet.